Hi, I'm Ijo. I work with Professor Park, and for this work, I also work with Professor Mish. Very excited to be here. So today, I'm going to talk about the heterogeneity of application resource demands that varies at fine timescales. As an overview, we first show that there are resource demand heterogeneity that exists within individual applications, and with varying resource demands, we can exploit resource-aware scheduling techniques in finer granularity. Then we present Harris Perf, a software profiler that we built to measure resource usage of individual function invocations. And even at 10 microsecond resolution, it incurs only 7 to 15% runtime overhead, or even lower. Lastly, we discuss future directions to exploit such fine-grained resource demand knowledge for the name of performance and high utilizations of resources. Then, just to set up a background, the resource demand heterogeneity refers to the observation that different applications exhibit different sets of needs for what people call shared architectural resources. For example, DRAM bandwidth, storage or network I/O bandwidth, L3 caches, which are shared among all the cores, and also pipeline resources, which are shared by hyper-threading siblings. For example, like a data analytic program may use more DRAM bandwidth than pipeline resources, while on the contrary, an object store server may utilize more I/O bandwidth. So knowing resource demands is important. Why? The primary reason is that sharing a physical instance with many different apps is so common in modern clouds, as well as scientific computing platforms. And when applications are co-located, they compete for different shared resources. Then, when contentions happen, it slows down programs. It also wastes other resources when particular contingent resource becomes a bottleneck. It also hurts the quality of services, as contentions may happen unpredictably. These are all well-known problems. Given the issues I just described, people have come up with techniques to schedule applications based on their demands. They first estimate an application's demand by some profiling or benchmarking, and then use these profiles to determine when and where to run the computation. For example, you can co-locate a memory bandwidth-intensive application like data analytics with a more compute-heavy one whose working set is small enough to fit in the cache. In this way, they don't interfere each other. But note that such characterization and scheduling mainly operate as a granularity of monolithic applications. However, what we found is that heterogeneous resource needs can exist within a single application. For example, consider a Lucene++ full-text search server. If you look at the DRAM bandwidth and instructions rate timelines, which are profiled as a resolution of 10 microseconds, you will see the resource consumption fluctuates over this short interval in processing a single query search. And actually, the red interval is associated with a function called createWait, which builds some internal evaluation rules for the search request. As you can see, the red region gets higher instruction rates, indicating more computes. And then the yellow region, the yellow region is about the function called score, which should go over the index documents in memory to actually perform the search. For the yellow region, as you can expect, the memory bandwidth is consumed more, while instructions keeps being low, as some cycles are suddenly be stalled due to more memory access. Looking at the stats average from 40,000 recorded invocations of these two functions, this trend is indeed valid among such many queries. Then, using this information, ideally, we could schedule createWait on a machine with higher CPU frequency and more pipeline resources, and we may want to schedule the score on an instance with more memory channels and co-locate it with other apps generating less DRAM bandwidth pressures. But the question is that, can we really disaggregate the monolithic applications and schedule such granular components separately and dynamically, especially without heavily rewriting the existing apps? In the past, it's hard, but now it becomes possible with the help of its emerging granular computing systems. These frameworks have a serverless nature, yet they can be also SIDful, like Quicksand and Granny. Such systems support live migrations of each small component And they can also manage a unified interface for both local and remote data access. So you don't need to worry about if the data is local or already migrated to somewhere else, as the system and libraries manages all that efficiently for you. For example, instead of packing monolithic apps to each machine, Quicksand breaks application into small shards that can be deployed across nodes. Therefore, such runtime systems unlock more flexibility for us to schedule small program pieces when they have different type of resource needs. Now, go back to our main topic of heterogeneity. There are two aspects to this problem: how to measure the resource demands at fine timescale in the first place, and secondly, how to exploit the heterogeneity, how to make use of that knowledge. For measurements, we present Harris curve, a profiler tailored for that purpose, and for exploit, we bring some prospective directions to this discussion, starting with measurements. The most straightforward way to measure the demands within an app is, of course, breaking the application apart and micro-benchmark consumptions of each part. However, such practice incurs too many engineering efforts. Also, if you break it apart, the locking and synchronization behaviors may be altered. You also may not get the most realistic input for each function in benchmarks. Given your resource data that deviate from the actual consumption at deploy time. So, we want to do runtime profiling without decomposing the application. And we can make use of hardware performance corners, PMCs, on modern CPU chips to gain the resource metrics. Then, more specifically, what are the requirements of a profiler for revealing fine-grained heterogeneity? First is, of course, high resolution, because as shown in the research query example earlier, the functions we're interested in may come and go very fast, down to microseconds to tens of microseconds. Secondly, we want to attribute the resource metrics to a function called timeline. So this not only reveals that function 0 is different from function 1, but say, if function 0 is reused by different components to do different things, we can also distinguish one invocation from the other. So we need a timeline. And lastly, the overhead needs to be low enough to not perturb the program behavior. Also, if we ever think of just-in-time profiling, in other words, if we can integrate a transparent profiler into the resource manager, it can automatically learn about the resource needs of deployed apps and adjust future scheduling based on that. In that sense, low overhead is even more critical. Then, we look at some most popular profilers that all use performance corners. First, Linux Perf, it does not have timeline support. Then, Intel VTune, it does enable timeline analysis, but when it runs with a small sampling interval, like 100 microseconds, it incurs up to 38% runtime penalty to the profile app, which is very high overhead. As VTune is a proprietary software that we can't fully understand, its overhead presumably comes from scanning the stack to track the control flow during the interrupts sent to the app. So we created Harris curve to achieve all three objectives: resolution, timeline, and overhead. How do we do that? We first talk about constructing the function called timeline. For this, we adopt an interrupt-free stack scanning technique from a prior work called LDB. Basically, LDB relies on compiler instrumentation to enrich each stack frame with a canary to avoid inconsistent reads of a frame that hasn't been fully populated or already destroyed. Then, LDB also added a monotonically increasing generation number to identify each stack frame, so that every invocation of any function gets a unique identifier on the timeline. And finally, the stack scanner can safely track the control flow of the threads without interrupts. So now we have a function called timeline. Then for the resource timeline, which relies on hardware performance counters to monitor the resource consumption, we can simply use a kernel module to send inter-process interrupts to APIs to pull the performance counter values. Such interrupts won't cause too high overheads as they complete instantly, because it just involves saving a few registers into memory, and then that's it. Now we have timeline data to perform various analysis to explore heterogeneity. So what's the overhead? As a baseline, VTune at 100 microsecond cooling intervals generates about 19 to 38% overhead. Yet at only 10 microsecond intervals, Harris perf only produces 0 to 8% from the stack scans, and an extra of 7% for PMC pooling. Note that here HotOS' runs with an order of magnitude finer granularity, and we still get much lower overhead. Then a further observation is that actually 99% of the overhead of pooling the performance counters are caused by the interrupts alone. So can we just get rid of all the interrupts? Actually, yes. We extended LDB's compiler instrumentation to let the program itself read the performance counters during function prolog and epilogs. We want to do function level analysis, so we use these two examples to calculate the change of performance counters during this invocation. Secondly, we instrumented the instrumented functions will self-report the performance counter values into the stack frames. There are actually some extra details here because an exiting function cannot write its final PMC values in its own stack, which will be destroyed soon. I won't cover that in this talk, but I'm happy to take follow-ups. And finally, our stack scanner, which originally is used to track the control flows, can now also pick up the counter values during the stack scans. So now we build the two timelines altogether. Preliminary experiments on this implementation shows no measurable extra overheads beyond just the probing effect overheads of stack scans alone. Now we have ways to reveal the heterogeneity. Then how do we exploit that? How do we make use of the knowledge? We bring a few prospective directions which all rely on granular computing frameworks intrinsically. Some of them are actively developed now in our lab. A straightforward use case is optimizing batch processing, where we have less contingent latency constraint and thus more opportunities to schedule tasks. For example, running a memory bandwidth intensive operation with a compute bound one, then we can see if we interleave the scheduling of the two tasks as shown in the bottom plot, they both run faster than being scheduled one after the other. Also, if a single task exhibits different resource needs across stages, we can also migrate them during runtime to always use the best fitting instance. Actually, some of prior works develop similar scheduling techniques for specific tasks with known resource usage patterns, like DNA training and Spark. Here, we are just trying to generalize this approach to generic programs with the help of profiling. A second direction is to ensure quality of services also with high utilizations. Prior works like Caladan has made a reactive approach where we ban cores from collocated best effort tasks when an increased queuing delay is observed for the latency critical apps. But with the knowledge of granular resource demands, we can now proactively schedule best effort tasks that just does not interfere with the latency critical ones. Then, this also better utilizes other architectural resources not consumed by the latency critical ones. And of course, you don't have to over-provision. The last direction for improving function as a service is more intuitive. As functions are naturally granular and fast containers are suitable for migrations, when a function is deployed the first time, some low overhead profiling can take place transparently to learn its resource needs, and then adjust the placement of container for later requests after we spin up a new container as somewhere else. A physical instance resource pressure shifts over time. That's fine. Containers can also migrate to keep conditions always low. And finally, in summary, we are targeting on applications with inherent heterogeneous resource needs. We can leverage on first, fine-grained profiling of resource demands, and secondly, scheduling flexibility of granular computing platforms, so that we unlock more potentials to optimize both performance as well as resource utilization. That's it. Thank you.
Hi, Jeff Mogul, Google. This is interesting work, and it's complementary to a number of things that I don't think you cited, but you might want to look into. One is work on having multiprocessors with the same instruction set on each node, but different size cores with different properties. So some might be good for in-order execution, but very low cost. Some might be good for like large-scale floating point stuff. And for example, the AMD big.little approach, I think that kind of thing is very heavily used in small-scale systems rather than server-class ones. Another thing that seems to be similar is the simultaneous multi-threading architecture, where you can, at very fine time scales, switch between different threads in the same core because of their non-overlapping resource contention. So I think you might want to look into how you can take the system you built and apply it, especially I think to the big little mechanism where you may be able to move pieces of threads around from core to core very quickly in order to take advantage of different resource provisioning on the cores, not just different resource demands by the applications.
Yeah, thank you. That's very insightful. Actually, we didn't think about like more smaller
follow-up
engineering. Yeah. Thanks.
I'm Sharia Patel, UBC. I actually wanted to follow up on Jeff's question as well. So there was in the SMT space and multiprocessor in general, there was a work from HotOS'25 which explored a similar problem, and in the end, what they found was that if you just account for memory bandwidth contention, you can reach within 2% of optimal. So I was curious to know, what has changed since then, which makes you want to profile more resources?
So your question is like, what has been changed after the work?
Yeah, what is the motivation that you have? Because they showed that memory bandwidth contention, just profiling that was enough to reach within 2% of optimal. So something has clearly shifted because now you're profiling more types of resource contention. So I was trying to understand what has shifted that makes you want to do this work.
Sure. Yeah, of course, the performance counters were designed for all kinds of architectural resources, actually not designed for memory bandwidth. Here we are just, for simplicity, we use bandwidth as an example. And the other difference is that I think now we have those granular computing frameworks that even if different hardwares have different offerings, we have better ways to breaking application apart instead of focusing on monolithic ones, so that we can optimize at a more granular level.
Just to add on to that, actually, from 10 years, more than 10 years ago, number of cores on server class machines has increased a lot. So that actually contribute a lot to the contention on the memory bandwidth. So previously with the servers with 20 core, memory bandwidth is never a problem. Now, each machine has more than 200 hardware threads, so it's much easier to get contended and combined with the big data another trend.
Yeah, and then also memory bandwidth is actually kind of special in terms of it's not like a cache that when you saturate you get slowed down. You get slowed down pretty linearly if your memory is it's a very memory bandwidth intensive app, even if it's not saturated. Yeah, that's what our experiment found. Yeah.
Hi, I'm Anna from ETH. Yeah, really interesting work. I'm curious, how often do you think you need to sample to get sort of accurate granularity?
I think it really depends on what specific application you are operating on and how detailed you want to go in terms of the granularity. In the search request example, we need to have 10 microsecond interval because eventually what we found is host those two components separately, and in the paper we analyzed that with other factors do they share the same states or something like that. So although those functions you eventually can break them apart, when you run a monolithic application, they may alternate between each other very quickly, and to see that you need the functional granularity. But once you already decompose that, or you just want to try optimizing function as a service, that's much easier in terms of granularity. Thanks.